Um, Last time I finished saying everything I'm going to say about conservation of linear momentum. So today, um, on to conservation of mechanical energy. Um, and so uh, one of the main scientific facts in just about every branch of science is that the total amount of energy in the universe never changes. It just moves from one type to another. Um, that's not exactly what we're going to be talking about here. We're going to be talking about a very specific application of conservation of energy under, very specific conditions. Um, so I want to start by just saying a couple things about energy. Uh, and then I'll talk about, I'll start talking about the different ways of measuring energy, changes of energy. Eventually, hopefully by the end of today, we'll get to this equation, and maybe next time, this conservation of mechanical energy. Um, so energy in general. Um, so the first thing is energy and any changes in energy, they have no direction. And so they're scalar quantities, not vector quantities. Um, so energy has a magnitude, but no direction. One nice thing about energy calculations is that sometimes in certain simple cases, uh, you don't have to do a full vector problem where you are thinking about a coordinate system and components and all that stuff. That can be sort of tedious in some cases. Sometimes it's easier to do a problem using forces and things, but at other times, problems are easier if you use an energy approach where you're just calculating a scalar value. And then the second thing about energy in general is the units always are a combination of mass times length divided by time squared. Okay, so that's a pretty messy looking unit. Um, Also notice that, sorry, the length is squared too. Now that's right. That's what I just wrote. That's right. But this is energy. So you can also think of the units of energy as being, so mass times length over time squared is force. So you can also think of this as force times length. Those are just two different ways of writing the same unit. That means that the SI units are kilogram meter squared per second squared, or newtons times meters. And since we use energy all the time, that's given its own name, the joule. named after some dead guy. And then third thing about it is energy is never destroyed. Only exchanged. Ooh, that sounded like Star Wars out for a second. Or transferred. Okay. The first type of energy that we're going to deal with, and kind of the most intuitive type, is kinetic energy. Kinetic energy, I'll just always write it Ke, is equal to 1/2 times the mass times the speed of an object squared. So this is the object's mass. This is the object's speed. If you have the speed, then this way of calculating it works great. If instead of having speed, you have velocity, because we deal with velocity a lot, you can also write this the same thing this way: 1/2 times the mass times the quantity x component squared of the velocity plus y component squared of the velocity. So notice you can sort of roughly think of an object's kinetic energy as a measure of how hard it would be to stop the object. Notice that's the same thing I said about describing the magnitude of the momentum, if you remember. This is sort of similar to momentum. Momentum was the mass times the velocity, and it gave an answer in a vector form, so momentum has a direction. Kinetic energy doesn't have a direction, but it's still just multiplying the mass times something having to do with the speed. So something big, fast, has a lot of kinetic energy. So like a semi-truck has a lot of kinetic energy. Something small and slow has low kinetic energy, like a snail. So a semi-truck has a lot more kinetic energy than a snail. Okay, so for example, how fast does a 7-kilogram bowling ball have to move to have 100,000 joules of kinetic energy? So 100,000 is equal to 1/2 times 7 times the speed squared. And we're just going to solve for that speed. So 200,000 divided by 7, b is equal to plus or minus square root of 200,000 divided by 7. Can someone tell me what that is? $169.03 meters per second. So over 300 miles an hour. So don't get in front of that. But notice that increasing an object's kinetic energy means speeding it up, and decreasing its kinetic energy means slowing it down. Because the objects, in this class anyways, the mass stays constant. You never do anything to the mass. So increasing an object's kinetic energy means speeding it up. And decreasing its kinetic energy means slowing it down. So the next energy-related quantity we have to talk about is work. And work is not an amount of energy. So it isn't an amount of energy that an object has. It's an amount of energy change. And this energy change has to be caused by the application of a force. Okay, so there are many ways to change an object's energy. One is to put it on a burner on a stove. That increases the temperature, increases the energy, but that's not what we're talking about. We're only talking about changes in energy due to applying forces. Okay, so that's what work is. And let's think about what we would expect. The relationship between the direction an object is moving and the direction the force would have to act to change its energy in different ways. Okay, so let's say that an object is moving towards the door. Okay, which way would you think, and And remember that changing its energy, its kinetic energy, that's what we're thinking of as energy for now. If you wanted to increase that object's kinetic energy and it's moving that way, which direction would you push on it? Yeah, you'd push in that same direction. To increase its speed, you'd want to push it along to help it, right? Like if you're running and a big wind comes behind your back, it makes you go faster, you know? If you're trying to decrease an object's energy, it's going that way, you'd want to push on it to try to stop it this way, you know, push it back this direction. So it makes sense that that the work done by a force on an object is going to be positive. It's going to increase the object's energy if the force and the velocity are in the same direction. And it's going to be negative. It's going to decrease the object's energy if they're in opposite directions. Okay. So now let's go to the mathematical calculation and you'll see how that works. So let the force vector, and I'll break it up into x and y components, be the force vector applied to an object. And lowercase d vector is the displacement vector. So I'll call that dx and dy. And let that be the displacement vector from instant 1 to instant 2. Then the work done by that force is equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement. That way of multiplying vectors is called the dot product, by the way. You don't need to remember that, but it's called the dot product. And notice that even though we're multiplying two vectors, the answer we get out is a scalar, which is good because all energy quantities have to be scalars. Yes, because right, work is a change in energy, so you have to be able to add work to energy. So they have to have the same units. Yep. So we multiply two vectors, but the output is a scalar. Okay, so let's do a couple examples just to see. So that's sort of a messy looking mathematical formula, but let's see what happens when we do it. So what if you had a force vector going this way and a displacement vector going this way? Would you expect work to be positive, negative, zero? Okay, yeah, so let's say that this force is 0, 1, and this displacement is 0, 1. Then the work would be 0 times 0 plus 1 times 1, and so we get 1 out. So that's positive, because those are in the same direction. Now let's say the displacement is still this way, but the force is the opposite direction. So this time it's 0, negative 1. Do you expect work to be positive or negative or 0? Negative, yep. So work is equal to 0 times 0 plus negative 1 times 1. So you get negative 1. You get a negative answer. Now, what if the displacement question? Well, it's a change in energy, so it means that so a positive value for work means that it's increasing an object energy, and a negative value means it's decreasing an object energy. Right, right. It's without saying anything about direction, it's just saying this force is trying to speed it up and this force is trying to slow it down. Right, no direction. That's exactly right. Now, what if you had a displacement this way and a force that's kind of in the same direction, like that? Let's say the force, let's say this is equal to 1, 1. Okay, they're like 45 degrees apart, but they're kind of in the same direction. Well, think about that intuitively. What do you think would happen to the speed of the object if you had a ball rolling that way and you applied a force at an angle, would the speed increase, decrease, stay the same? What do you think? It would increase, and so we're still going to get a positive value here. Um, so work here is equal to 1 times 0, which is 0, plus 1 times 1. So we got back 1 again, positive. So any of these where you get a positive value for work, it means the speed would be increasing. Negative value means speed is decreasing. Well, what do you think would happen if I did that force not exactly in line with it, but kind of in the opposite direction? Positive, negative, or 0? It would be negative, yeah. So the one thing that we haven't thought about yet is, what if you have a displacement like this, and you have a force that's exactly perpendicular to it? Well, in that case, so we'd have negative 1 times 0 plus 0 times 1, and you get 0. Okay, so if an object is moving, well, if a force is applied to an object that's perpendicular to the direction it's moving, that force does no work. It's not doing anything to increase or decrease the speed at that instant. Okay, so these are sort of the big take-home ideas. Here are the intuitive results. First, if the force and the motion are mainly in the same direction, then work is positive, and the object speed, well, or the force is trying to increase the object speed. Let's say it like that. There might be other forces that are keeping it from achieving that goal, but this is what that force is trying to do. So the force is trying to speed the object up. Second, if the force and the motion are mainly in the opposite direction, then work is negative, and the force is trying to slow the object down. And then the last important result is if the force and the motion are perpendicular, then the work is equal to 0, and the force doesn't, I'll just leave it like that. But what that means is that the force at that instant is not trying to change the object's speed. Okay, so every kind of force does work, but now we're going to split up forces. So every force does work. But we're going to see that it's helpful to us to split up forces into two different categories. Those are conservative forces and non-conservative forces. And the reason we're going to do this is so we split them up because it's generally easy to calculate the work So it's easy to calculate the work done by conservative forces. And it's generally hard to calculate the work done by non-conservative forces. Okay, so we'll see that this isn't always the case, and there are some non-conservative forces that even when they are producing a force, they don't do any work. But overall, if you had to choose a category to deal with, you'd rather deal with conservative forces than non-conservative forces. And so this is going to be an important distinction to make. And so I'm going to first talk about what conservative forces are. Um, and a conservative force is a conservative force is one where knowing an object's location is enough to know the force that's applied. Okay, so um, the easiest example is gravity. Gravity is a conservative force. So um, say you know the mass of this calculator. Let's say it's 0.1 kilograms. And now, if I tell you the location of this calculator, is that enough information? With no other information, could you tell me the force that gravity applies to this? The answer is yes, and actually the answer is you don't even have to tell me the location. I just know that the force is 0.1 kilograms times 9.81 meters per second squared down, right? Whether it's here or whatever, right? You understand what I'm talking about? So,
But technically, it's a little,
in what way?
when it's up here, it's a little.
Oh, that's true. Well, so we haven't talked about the more complicated calculation of gravity, but if you were using that, it would still be the same thing. Then you would need to know the location, but that would still be enough information to know. So the question is just, if I tell you the location, can you tell me the force? And gravity works that way. Okay. Another way of expressing that idea is a conservative force is one that you can express as a force field. Um, so what is a force fields sound cool because they talk about them in like Super Friends and stuff all the time, but they're not really that great. They're fine. But the idea of a force field is no matter what location you go to, since a single location corresponds to a single known force, right? Like if this thing is at this location, that corresponds to a known force of 0.1 times 9.81 down, right? So since there's that correspondence, you can think of it as just the entire room or the entire world is just full of forces pointing down with a magnitude of 0.1 times 9.81, just waiting for this calculator to get there and claim it, you know? It's so there's a force, a latent force sitting at this location doing nothing until I put the calculator there, and then it's like put into effect, you know? You can think of it that way. And so they call that a force field the same way like a field of daisies or something, you know, like wherever you go, there's a daisy, you know, there's one, you pick it up. This is like wherever you go, there's a force. Go over here, there's that force applied to this thing. In this class, there's only one other example of a conservative force. So there's weight, and then the only other one, and it might seem sort of like an odd, like weight comes up in every problem. This other one hasn't come up in any problem so far. But the other one is spring forces. So like if you imagine a spring attached to that wall, okay, and you do some careful measurements of how stiff the spring is, and then you attach it to this calculator. So this is attached to the wall by a spring now. And if I pull it back this far, the spring's going to try to pull it back this way with some known force. If I put it up here and compress the spring's going to try to push it this way with some known force. And the key idea in these cases is path independence. It doesn't matter what the path is you take to get to that spot. So like if this is attached to the wall by a spring, and I go like this 50 times and then move it to here, the spring's still going to apply the same force to it that it would have if I would have just moved it there in one step. Okay? Nothing's changed about that force because of how I got there. And it's the same with gravity, you know, like there's a gravitational force waiting for this calculator at this spot, and it won't change if I do this 100 times. It's still going to be the same value when I get there. Okay. So you can think of this as being equivalent to a force field. In this class, there are only two conservative forces we're going to deal with. Those are the weight force and spring force. And there are a lot of other types of conservative forces, but these are just the only ones we're going to deal with. Magnets apply forces to each other through field forces. Those are conservative forces. If you hold a magnet up over here and hold another magnet here, you get the same force as if you do this for half an hour and then put it here. So that's a force field, and those are conservative forces. So what's a non-conservative force? Let me give some examples of forces where that isn't the case. So what's an example of a force where knowing the location of an object is not enough to specify a force? Okay. Well, the first one is friction. So, for example, let's say this is the location, and I tell you the location of this calculator is going to be right here. You tell me what the force vector is that's going to be applied to this calculator. Okay. Well, what if the thing's sliding this way when it gets to that spot? Then the friction force vector is like this, right? Now think of it still gets that same spot but sliding this way. In that case, the friction force vector is the other way. So those are two different times where this calculator is at the same spot, but that force was opposite. Okay, so friction force is not conservative. Knowing the location of an object is not enough to know the friction force. Any questions about that? This is kind of like philosophical stuff. I mean, like if you just want a practical answer for like how do you know a friction force isn't conservative, you can just look at the list that says, yep, it's not weight and it's not spring, so there you go. But this is just trying to sort of like explain how this works. And then like a normal force is another one. And that one might not be as clear at first. But say that this is the location of the object. Do I know what the normal force is? No, because right now the table's pushing up on it with 0.981 newtons, up. But now say I push down on it with 5 newtons. I haven't changed its location, but now the table's pushing up on it with 5.981 newtons. So without changing the location, that force changed. So it can't be conservative. You can't do anything like that with gravity or with spring forces. No matter what you do to it, those are still applying the force that's just specified by the location. Um, for conservative forces, um, there is a function called potential energy. There is potential energy. Um, that depends only on the object's location. And the thing about potential energy, like basically the idea here is we broke it up into conservative and non-conservative forces because conservative forces, it's easy to calculate the work done by those forces. Non-conservative forces, it's hard to calculate the work. Here's why. You have this potential energy function that only depends on the object's location, and the work done by a conservative force is equal to negative change in potential energy. Okay, so what that means is you can calculate the work done by a conservative force knowing over some amount of time, over a second or 5 minutes or whatever. You can calculate the work done by only knowing the location of the object at the first instant and the last instant. Okay, so that's a big deal. So that means you can calculate the work done by a conservative force given only the object's location or locations at instant 1 and instant 2. Okay, here's what the potential energy functions look like for weight and spring forces. The potential energy due to gravity, the gravitational potential energy, is equal to the mass of the object times 9.81 meters per second squared times the object's height. So this is the object mass. This is 9.81 meters per second squared. And this is the object's height. That's a good question. That is going to be an important point. It turns out that you can choose your H equals 0 to be anywhere you want at the start of the problem as long as you're consistent through the whole problem. And since we're only talking about, like if you look at that definition of work, we're talking about changes in potential energy, then that change just means that that constant, that arbitrary constant that you chose would cancel itself out no matter what it is. So H equals 0, you set that at the start of a problem in a way that's convenient to you. And then for a spring, the potential energy function is 1/2 times this constant K times x squared, where K is called the spring stiffness. And that has units of newtons per meter. Well, force per length. In SI units, it'll be newtons per meter. And this X is the object's distance from the spring's resting length. That's sort of confused sounding. But that just means that, so if the, so the spring has a length, like if you sit it on the table and don't apply any forces to it, it's this long or something, depends on the spring. So if you attach one end to the wall and then attach a mass to the other end, and then set the mass in a place where the spring is still at its resting length, the potential energy of the spring at that instant is zero. X is zero because it's at the resting length. Okay, and so since X is zero, the potential energy is zero. And the more you stretch the spring or the more you compress the spring, the bigger that X value gets. And the bigger the X value gets, the bigger the potential energy is. Any questions about that? In sort of a loose kind of sense, potential energy tells you how much danger you're in being near the object, Like if you take a paint can, an open paint can, full, and you put it here, you know, it's less of a concern to you than if you make your H bigger. As you lift it higher, MGH gets bigger, and the higher it goes, the more damage gravity could do to you when it decides to pull it back down. You know what I mean? Same thing with a spring. Like if you're sitting here and somebody attaches a knife to a big spring, when it's at its resting length, it's fine. It's just a knife sitting there. But if they stretch it to here, then if you got in its path and someone happened to let go of it, it could hurt you. If they stretch it to the end of the room and let go, it could go right through you or whatever, You know what I mean? That's happened to me before. Yeah. Yes. It's just the difference, exactly. It's how far you've stretched it or how far you've moved it in one direction or the other. Yeah. Any other questions? Okay, so that's kind of all we have to say about conservative forces. We're only dealing with those two. So now let's talk about non-conservative forces. So a non-conservative force is one that depends on other things besides the object's location. It might depend on the object's location too, but it has to depend on other things as well. Some examples. Well, in this class, it's easy to know whether you have conservative or non-conservative because anything that's not a weight force or a spring force is non-conservative. But examples are, the ones I gave are friction, normal force, and most types of forces are non-conservative. Normally, we don't like non-conservative forces because it's hard to calculate work for non-conservative forces. So usually, hard to calculate the work for non-conservative forces. But there are two important cases where it's not hard. And actually, so work is equal to 0 in two important cases. Okay, so that's good. I mean, that's even better than a conservative force if you just know that no matter what the magnitude of the force is, what direction it is, the work is going to be 0. That's, that's an ideal case. So the first one of those is a normal force for an object that's sliding or rolling. Work is equal to 0. And why is that? Well, remember when I was talking about sort of the take-home messages of that work calculation? If a force and if the motion and the force are roughly in the same direction, work is positive. If they're roughly in the opposite direction, work is negative. What happens if they're exactly perpendicular to each other? Work is equal to 0. And so think about the directions here. If this calculator is sliding along this surface, like as it's going this way, what's the direction of its force? I don't know, it's motion. Its motion is that way. What's the direction of the normal force? Up. And so those are perpendicular to each other. No matter how fast it's going, what's stacked on top of it or whatever, the motion and the force are perpendicular, so the work is 0. So that's great. And the other example that comes up pretty, question? If something is rolling or sliding, yeah, that's right. Along a horizontal surface, I guess. This is true, the normal force thing is true no matter what angle that's at. Gravity, it's true for anything that's moving horizontally, yeah. The second one doesn't come up as, normal force comes up all the time. This one isn't as common, but any centripetal force, so any force toward the center of a circular motion. Work is equal to 0. So why is that? Like imagine the case of so let's say there's a ball on a string being spun around in a circle. Okay. What's the direction of the velocity at this point? Well, that's hard to describe, but it's this way, right? That's the direction of motion. what's the direction of the force applied by that string? Toward the center. And so those two, again, are perpendicular to each other all the time. And because of that, that string doesn't do any work. Any questions about that? So any other kind of non-conservative force is kind of a pain to deal with. If you have friction in a problem, it's a pain to deal with. But problems of rolling or sliding along a surface or circular motion where a cable is connected to the center of the circle, those are two examples of non-conservative forces that don't cause any problems at all. They just go away. Even though those forces are non-zero, the work they do is non-zero. The forces are non-zero, the work is zero. Yeah. Okay, so now we're finally at the equation and we can do some problems and stuff. So conservation of mechanical energy. So if non-conservative forces do zero work between instants 1 and 2, then if you add up the kinetic energy and the potential energy of an object at instant 1, that has to be equal to the sum of the kinetic energy and the potential energy at instant 2. Um, and so this allows uh, calculating relationships between speed and position. Um, mostly for problems involving sliding or rolling or swinging. So as far as when to use this equation, because this is the first topic that we've discussed where there are other ways to usually approach questions that you can answer this way. But if you see a problem that's rolling or sliding along a surface or swinging, and you're trying to calculate, either you're given a position and you want to calculate a speed, or you're given a speed and you want to calculate a position, that's a slam dunk for this approach. Okay, so that's how to identify these problems. Anybody have any questions before I do an example? Okay, so let's say there's a skier at the top of this short little hill. And let's say the hill has a height of 5 meters. It's just part of a hill. And let's say the skier has a mass of 50 kilograms. Skier starts at rest. What's the speed at the bottom of the hill? The key thing here is that we have to assume there's no friction. So it's kind of amazing that we're able to do a calculation like this with so little information. Notice it doesn't say anything about the shape of the hill. Isn't that bizarre? Like, this hill could do this the whole way, or it could just barely drift down until it drops off really fast at the end, or it could drop off really fast here and then be flat the rest of the way. Any of those, any hill you can make where the skier would actually get to this point, if there's no friction, you'd get the same speed at the bottom. And that includes there not being a hill and him just jumping. The speed is the same at this location. And if you try to think about how you would have to use Newton's laws to do this calculation, it would be a major pain. You'd have to have some representation of the shape of the hill. And then you'd have to use calculus anyways at the end to come up with to take all the accelerations you calculated and turn them into a velocity. But we're going to do it in just one simple one-line equation using conservation of mechanical energy.
So the speed that we calculate after doing this would be the same speed if we did the crazy second law.
Yeah, that's right. But you couldn't do it without calculus, and even then it would be a major undertaking, you know. It is. That is the answer. But that's not how we're going to think about it. Because the approach we're going to take is like works in more generality, you know. Like we could also, you could combine problems with gravity and springs and stuff, and you couldn't do that. But yes, you're exactly right. No, you're totally right. It doesn't always have to be decreasing, but it can never go higher than the starting point. So he could go down and then go up a little hill and then, yeah. But if there was ever a point where it got higher than that starting point, then he'd be stranded in that valley. Okay, so like we were talking about before, you get to choose an h equals 0. Let's choose our h equals 0 to be here. Why not? Whatever you choose as your zero height, that is to be the zero height for the whole problem. And now I'm just going to set it up a little table with instant 1 and instant 2. Oh. Okay, so at instant 1 on the top of the hill, and I'm sort of rushing through this actually. The first thing you have to do is make sure that conservation of mechanical energy is going to work for this problem. So what forces at some arbitrary point in this path, what forces are going to be acting on the skier? Weight, a normal force, and nothing else. That's it. Just weight and the normal force. Since we're ignoring friction, that normal force does zero work, and so we can use conservation of mechanical energy. Okay. So the potential energy, gravitational, is equal to the mass of the skier. So 50 times 9.81 times the height at instant 1, 5. And so that is, I believe, 2, 4, 5, 2.5. And then the kinetic energy at that instant is 1/2 times the mass times the speed squared. What's his speed at the top of the hill? 0, yep. And now instant 2 is at the bottom of the hill, so the gravitational potential energy is 50 times 9.81. And what's the height? 0. So there's no potential energy there. And then the kinetic energy, 1/2 times the mass times the speed squared. Do we know the speed at the bottom? No, that's what we're trying to calculate. So I'll just leave that as v squared. And so conservation of mechanical energy says 2452.5 plus 0 is equal to 0 plus 25 v squared. And so that is 98.1, right? 98.1 is equal to v squared. Is that right? And then, so v is equal to plus or minus, what's the square root of that? 9.9 meters per second. So at the bottom of that 5-meter hill, the skier's speed is 9.9 meters per second. Any questions about that? Okay, here's a question for you. Now say that this skier, instead of being dropped off at the top of the hill, gets a ride behind a truck to the bottom of the hill, okay? And he's just gonna like let go of the bumper and ride the momentum up to the top, okay? That's how he's going to get to the top of the hill. How fast do you think the skier would have to be going at the bottom of the hill to make it exactly the top of the hill with zero velocity, zero speed? Well, there's a speed at the bottom where, so gravity is going to make him slow down and slow down and slow down. And if he's going just the right speed, he'll slow down to the exact point of being at rest when he gets to the top. Can anyone do that in their head? Well, it's a trick question because all we're doing is flipping these two instants. You know, our instant one now is the skier with zero potential energy at the bottom of the hill with a speed of v, and instant two is at the top of the hill with this much potential energy and zero kinetic energy. And so the answer is exactly the same. You know, it's just like we flip the sides of the equation. It's the same equation. And so if the skier was going 9.9 meters per second at the bottom of the hill, they would come to rest exactly at the top if there's no friction. Any other questions about any of this? Okay, that's it. Have a good weekend. Your test, I know. Today, it'll be done. Yes. Bye. Oh,
What day is the final?
Thursday at 11.
On the 20th?
Yeah.
Tried to wrap my head around all this.
Oh, yeah.
It's a little high.
Energy is pretty weird. Yeah. 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 Work is a change in energy caused by a force application. Yep. Yep. The units work out. Right. Yeah. Right. Exactly. Bye. You too. Hi.
So I'm going through
Okay. Yeah. 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 For sure. Is next week okay? Sometime? Sure. Okay. What is there a day that's better next week, or do you want to just wait and see how things pan out a little and then let me know? Why don't you do that then? Yeah. Okay. Okay. Sure. Hi. Yeah.
So I was looking back on the syllabus. I guess I was
Okay.
but is it that you only 92 to 100 days?
It'll be probably
90 to 100 like normal class?
it'll be lower. Yeah, it'll go a little
I was
lower.
gonna say it seems weird that like the top 8%.
It's 8, 10, 10, I think.
One of them's 12. Has like and 82.
Oh yeah. Uh-huh.
Yeah. So do you think it'll be like that? Or do you
I don't
it's
think
like
it.
normal, like,
I think if you think of it as sort of 90, 80, 70, that'll be pretty close. I mean, it always sort of depends. I adjust it a little at the end depending on how many people I have where and that kind of thing. But yeah, the grades are a little on the low side this semester, so everything will be relaxed a little bit. Mm-hmm. Yeah. Yeah. Right. Yeah, you're applying to colleges right now and stuff. Yeah.
So that helps the
Okay, yeah. Right.
I understood the material.
Yeah.
I was like, if I didn't understand the material, you teach it and it sums it up.
Yeah.
So like I understand it.
Mhm.
Do you think there's gonna be any like opportunities for extra credit or
No,
like
but
you're saying on
remember that a good final bumps your grade up a ton because it not only counts as a test, it counts as a second test and
Right.
replaces a low score.
Okay.
So with a
right now, like each
like I
test
don't
is
remember if
17
you
and a half points out of it.
yeah, but and remember that excuse me. So I don't remember what your lowest score is. Did you have any scores that were lower than other ones on tests, or they all been pretty much? Okay.
It's so hard 'cause
So like if you had one
yeah.
lower score and then say you got a good, like an A on the final, it would count as a A, so that would pull your score up a little. But then it would also erase your one low score and
Okay.
replace that with an A, which has a huge effect on your overall grade. So
is
doing
there
well
like-
on the final can bump your
Right.
grade up a lot at the end.
Right now, I guess like each test is
Right.
14%.
Yes. Yeah.
That's good.